zkVot is a fully anonymous, censorship-resistant voting protocol built with Mina.
And some other technologies in such a way that achieves something that wasn't possible before, I guess, which is full censorship resistance. Till now, all the protocols had some limitations around censorship, and it actually depended on number of voters voting. But with zkVot, you can have 2 people voting, or you can have 100 million people voting. It stays the same. It's fully anonymous, it's fully censorship resistant.
So just to play that back, what makes it unique is that it's both anonymous and censorship resistant, and it scales.
Exactly.
How does that work?
The main idea behind is modularism, which is using different technologies for each specific part of the architecture. In order to achieve anonymity, we have client-side proof generation, which is, I believe, the only way of achieving full anonymity. Because if you store something somewhere, at some point it can be broken. But with zkVot, it doesn't depend on the decryption side because you don't actually encrypt anything. You just generate a zk proof. Even in the future, like there are quantum computers enabled, will just break the soundness, but nothing will happen to the past elections. So I think that's quite interesting. In the liveness censorship-resistant section, we are using separate DA technologies from Mina. Data availability is a very new concept, and I believe that till very recently it wasn't really fully possible. But with evolving technologies, right now we have light nodes, and both while accessing the chain and reading through the chain, you can achieve full censorship resistance. So basically, once you gossip a vote out there, it's impossible for it to get lost, at least for like 24 hours or a few days, which is really important. And it gives you enough time to count those votes and actually finish the election. And we have the counting process, which is, again, interesting, I believe, because it achieves scalability through having permissionless setup. So it's quite opposite to what other rollups do. In rollups, they try to achieve scalability through having only one sequencer. And they say that since we have a very big and strong sequencer, we can have very good TPS.
zkVot is just the opposite. They have a permissionless setup. Anyone can come and count the votes and participate in the election, even from their mobile.
And right now, with our current numbers, counting around like 1 million votes in full parallel setup takes around like a few hours, 5-6 hours, which I believe is very, very scalable. Because you are actually aggregating all these proofs together in a single zk proof of constant size. And once you have that proof, you don't even need to settle actually. If you need long-term liveness, you can settle on Mina so that election results live on chain forever. But let's say it's a very small short election, you can even store that proof off chain. I believe that's also important.
Time to dig deeper.
So there are 2 types of proof that we generate. The first is the vote proof. So basically, each individual voter needs to generate a proof of their own, and that cannot be delegated to anyone else because that should stay anonymous. With a regular browser, that takes around like 10 to 15 seconds, which I believe is very ideal for a voting setup. And once you have all these vote proofs, you need to aggregate them. And there we had this issue that we need to aggregate them in such a way that we also
make sure that none of the votes are repeated.
Each vote is identified with a nullifier, which is basically an anonymous way of tagging something. We know that they are unique if the nullifiers are not the same, but nullifiers don't reveal anything about public keys. And the problem is that while counting those proofs in parallel, you need a way to actually combine them without any nullifier repeating. And if you make that check linearly, then that's very expensive. Because let's say I have counted 100,000 votes, you have counted 100,000 votes. While we are combining, we need to make sure none of those votes are repeating, but we don't want to check each vote repeatedly. And we achieved that through a different tree structure. Actually, we designed our own tree in zkVot, which uses a few different structures, a Merkle map wrapped around the segment tree, and also with some square root decomposition, allowing us to achieve full parallelization. So in an election of n voters, for instance, you can have square root of n counters. Each of them count votes as they come in. So you don't need to have votes available at the time of count, which is again very important because in that, like, that's a real life election, so won't all votes come at the same time. So they'll be coming gradually. And while they're coming, each of these parallel threads can count them. And once they all have their own separate trees, they can just combine them in logarithmic time.
Can you talk a little bit more about the interaction with Mina and the tooling around Mina that makes this possible and where the interaction points are?
So the first tooling we use is O1JS. O1JS is quite strong in that case because it's actually designed around full parallelism. While you are doing parallel proof generation in other proof structures that are available today, as you have more and more proofs included, the proof size increases. Even the proof size is constant or very small, the steps in between are getting bigger, which is an issue. But with zkVot, it's not the case. Regardless of how many votes you have in a single step of the voting process, it's always the same proof size, so that you can gossip them quite easily, which is around like 4 or 5 kilobytes. So that's also very small and very fast to gossip. And then through the pickles layer of O1JS, we aggregate them very, very fast. Right now, in a regular browser, aggregating takes around 15 to 20 seconds to aggregate any set of votes. And yes, in that we come up with a single O1JS proof. That is fully off-chain. It has nothing to do with Mina per se. It's just O1JS. And then once we have that final proof, we send it to the Mina. And on Mina, we have a separate layer to achieve full censorship resistance. So as you recall, before I said that the aggregation network is permissionless, so anyone can count votes. But then there's this question, how do we know that someone is not censoring any votes? Maybe I said I have counted 100,000 votes and that was all that I had, but maybe I'm lying. I didn't count a few votes. So how can I actually make sure that I have all the votes? And just to highlight there again, I can't be lying about the number I have in terms of minimum. If I have 100 votes available, I should have at least 100 votes because I can't generate votes from scratch, from zero. But there can be more votes available that I didn't count. And in Mina, we achieve that through a condition that we have created that we call the accepting the maximum condition, which is basically supported by having multiple people settling at the same time and always choosing the maximum of them from the history as well. So let's say you send 100 votes aggregated. I send 105 votes and Matthew sent 110 votes. Then the protocol chooses 110, records that results, and also records the number saying, okay, till now we have received 110 votes. But the protocol, Mina, doesn't know which 110 votes it has. And then someone else comes and says, I have 120 votes. Maybe before Matthew was censoring some of them. Maybe some of the votes weren't available at the time of his aggregation. Right now we have more votes, so protocol accepts that one as being bigger than. So the proof updates on the chain. And that's where we use Mina the most to achieve censorship resistance at the end of the election. And if you wait a long time enough, then you make sure that like you have all the votes available recorded on the Mina chain. That's the main point of using Mina. And I believe there are two interesting points about that. First of all, I don't know if this is a valid consideration, but I always say that Mina is like a data evaluate layer also because it has super light nodes. And basically anyone can submit a Mina transaction without any censorship issue because, you can have browser nodes, even browser full nodes. Mina has a very limited available data storage. So you can store unlimited amount of data. But I don't believe that's one of the requirements of DA. DA should be live, should be accessible, but it can be a very small DA, but it's still DA. And we use Mina as a DA here. We know that number of aggregators is limited. Not everyone will be aggregating. And Mina's block space is enough to make sure that there is enough people joining in the network, joining in the aggregation process, and then to make sure there is no censorship happening on that side of aggregation. And a second thing is using the usage of preconditions on top of Mina. Right now, it's not fully implemented because it's not available on the Mina L1. We will be having this accepting maximum condition as a part of the core protocol. So the Mina network will be asserting that the proofs being bigger than each other without accessing the state. So it won't even read the state. It will just make sure that it's bigger than the state without accessing the state, which is quite powerful because like that, you actually get rid of any concurrency issue happening because of your proof generation time. So let's say I have submitted a proof of 200 votes, but I paid very, very little gas fee. So like I didn't include in a lot of blocks. But once I have included, I will be passing that proof. Even I have generated proof like hours ago, it is still valid because it's just asserting being bigger than the state, and it is still bigger than the state.
Next, please could you explain why you call it a protocol and not an application?
So I'm not sure about technical definition, but to me, a protocol is something that consists of separate layers. So each layer can be replaced without affecting any other, as long as the protocol rules are staying the same. And by protocol rules, we just mean some common communication rules. Let me give you the most common example, internet. In internet, we use a lot of protocols, and the one that we most often use is HTTP, HTTPS. There are different parties like the server, the client, some service providers, or even some like client-specific providers like VPN. Servers, they don't know if you are using a VPN or not, but you can just plug in a VPN or plug out without affecting any connection in between. That is because everyone is using the same common understanding of communication. So there are some rules, and if I am sending the protocol in the correct sense, then others understand. So there is this header field, and in the header field, I define a type. If I say that's a GET request, and everyone knows that's a GET request, and they accept something very specific from it. If I don't follow the rules, they just ignore my transaction, my internet transaction at blockchain. It is the exact same for zkVot. That's why we call it as a protocol, because zkVot can work without any layer in between. Like you can plug in any layer that you like between different layers, or you can just take out a protocol, take out a layer from the protocol. Of course, each layer is crucial. If you take out one, maybe you are losing some censorship guarantees or some scalability guarantees, but still like you can do it in some specific use case. Let me describe layer by layer. At first, we have the client-side layer where we generate proofs, again for anonymity, but also scalability, because in zkVot, every voter is generating their own vote, and that's very scalable. because the proof computation limitations of the network is scaling with number of voters. So with each new voter, we actually have more computation power available. So the proof generation time doesn't change in the client-side layer. That's like full scalability that we can achieve right now. And then once those votes are generated, we need to gossip them to the environment. So I have the vote that's anonymous and it should be counted. Think this as a regular election. I have like created my vote, my ballot, I put my stamp on it, and now I will put it on the box. And the box in our context is the DA layer. It's quite interesting again that we can actually use any DA layer that we choose as long as we don't mess up the proof system that we are using. Right now, zkVot is supporting two different DA layers, Celestia and Avail at the same time. You can even use both of them at a single election. That's even possible because aggregators can actually read through different layers at the same time as well. So you can submit your vote to Avail or to Celestia or both of them at the same time. It just doesn't depend. And then you gossip the vote. You pay the gas fees for the DA layer, for the availability, and you know that the vote will live for anyone to read for a meaningful time. And in an elections case, a meaningful time is like a few days for all votes to be counted. So right now we have the ballot, we put it on the box, and we want someone to count it. And that is the counting layer. In our technical terminology, we say this is the aggregation layer because we actually need to combine all votes as a single proof. We can, of course, count all votes one by one and put that on the chain, but that's not really scalable. It's actually very similar to a zk rollup in that sense, but it's a decentralized zk rollup. We have a lot of different transactions, different votes happening, and we are rolling up all of them into a single vote. That is the aggregation layer. And the cool stuff that we discussed before, the new tree and the parallelization, etc., all that happens in the aggregation layer. That's fully permissionless, and aggregators can communicate to each other in any way they choose. Right now in zkVot, we don't specify a specific protocol for those aggregators to talk to each other. But since they're operating independently and the memory requirements between them is very low to transfer proofs, since proofs are really small, it's not quite hard to describe any protocol that will work in between those aggregators. So aggregators talk to each other. They read votes from the DA layer. They count, they aggregate them. And in the end, they come up with a single proof of all the available votes until now. So maybe some future vote will arrive. As they arrive, we can integrate them to that proof in almost constant time complexity. It's not a problem. But for now, we have a result and we want to settle the result. Before settling the result, we actually already have a result that is soft finalized. I think that's the proper terminology. It's actually really similar to the tally process in regular elections. So in most of the countries, in regular elections, there's a party that's called tally man. So basically anyone wanting to like observe an election can go to a ballot and observe those votes counted. So they opened the ballot, they took out each vote, and they count the votes by showing to everyone. And in zkVot, the aggregation layer does this exactly, or even better, because you don't access your own ballot only, but you actually access all of them at the same time. Because there's only one global box that everyone put their votes in, which is the DA layer. So everyone observes this process, everyone sees them counted, and they have the soft finalized result. In zkVot UI today, we also reflect this portion of the election, and you can even see results before they are submitted to Mina. But of course, soft finality is not enough because in the long run, it just becomes very centralized. Because like if I have 100 million votes, for that election to stay censorship resistant, all of those votes should stay available for all the time, which is something very bad. That's why we count them at the first place. So we need that counted final result to be settled somewhere. And there we have the settlement layer, which is Mina. As we described before, in Mina, we have this condition AMC, accepting the maximum condition, which allows us to have censorship resistant while shrinking those results from aggregating layer to the Mina. So if you think about it from like a 2D perspective, there's the client, it's distributed, all client converges to a single DA, and then the DA distributes again to different aggregators. They talk to each other, and on top of the settlement layer, Mina, they reconverge again into a final combined result.
When we say there's different aggregators, if I'm understanding it correctly, anyone can be an aggregator.
Exactly.
The other maybe crypto adjacent term is sequencer. Is that fair to say?
So in the sequencer, there's a sequencing. So they also decide on orders that they aggregate. In our case, it's also a sequencer. But since with votes, the sequence, the order is not important. That's why we call them aggregators.
Yep.
But a sequencer is also equivalent in our.
In the current state of where Mina is and how the product works, it takes 15 seconds for a user to submit their vote. What is the time limit between we get to that vote and the user can see where the current soft finality is in terms of like the polling?
Like 30, 40 seconds.
30 or 40 seconds.
Because like the block time of DAs are usually around like 8-10 seconds. So assuming that you were included in the first block, which is usually the case, that's the point of DAs. You can actually make your vote heard by anyone in like around 10 seconds.
Yep.
And in your browser, through a light node, you can connect to the DA right away. And all 1JS proofs can be verified in the browser. So you don't actually trust in anyone.
Yeah.
You verify the soft finality result in your browser as well. Soft finality cannot be wrong. It can be just less. So maybe you skipped some vote, and with the DA there was an issue. You weren't listening properly, so you don't see the whole result. But the result that you see is true.
Interesting. Does that 40 seconds matter in terms of the quantity of votes that are being processed? Let's say like if there's the difference between a 100-person election, 1,000-person election, and 1,000-person election right now.
So there are two limits. One is the DA limit, so that's an issue. But with the current setup, the limitation over DA is really, really high. Plus, with zkVot, you can use multiple DAs at the same time to actually boost your TPS performance. You can increase it in some ways. So I don't think that's the bottleneck. The other thing is the proof verification time. If you want to like get these soft finality results and verify all of them in your browser, that can take some time. But there are some statistical methods to improve that time dramatically. So basically, if you get those votes and put them in a random order, you don't need to check them all.
Yeah.
You can just, check 30, 40 of those with 99% confidence. Most of them are correct if you didn't find any unvalid ones. That's basic statistics.
Can we talk a little bit about, could this work on other networks, or what makes it special to Mina specifically?
So with other networks, first of all, there is no 1JS. That was the first reason why we have chosen Mina. Other networks are not designed to verify zk proofs that efficiently. So it can be quite costly to actually make sure there is censorship resistance through having a condition on the L1. If we were to replicate the exact same mechanism on Ethereum, then we would need Ethereum to verify like limitless amount of aggregators. Of course, they pay their own gas fees, but if the gas fee is higher than some specific amount, then it's not permissionless anymore. It takes like $10,000 to actually verify the result on the chain. Not everyone can count. They can generate the proof, but they can't settle. With Mina, it's the same cost. It's like less than $1 to actually verify the proof. So literally anyone can count and anyone can settle. The second reason to choose Mina is the constant block size. With zkVot, long time censorship resistance is really important because we are doing like a country-wise election. After 100 years, that result will still be important. So we don't want that result to be more centralized. With most of the blockchains, as time passes, there are more and more blocks. The blockchain becomes more centralized. And it depends on number of archive nodes storing that information for you to re-access that information, which can be unavailable after some amount of years. With Mina, that's not the case. The proof size is always the same. And by storing like 10 kilobytes in your computer, you can make sure that it becomes as censorship resistant as of that day as today. So like there is nothing changed in that time interval. So 100 years can pass, but the censorship resistance will stay the same. That is settled on Mina because Mina has a constant size.
Just to replay that back, constant time verification, making it cheap and accessible for anyone to be able to verify. And then the fact that Mina will always remain a constant size as a settlement layer into infinity, as long as there's no Armageddon and someone's running in one computer somewhere.
Exactly. Maybe a final thing is very light full nodes. I think technical terminology is like super light nodes of Mina. They are even lighter than light nodes of the layers. Yeah, right. It's true. Like right now.
No, I'm laughing just in that we can't find better names for these things. But super light node. That's great.
Yeah. So that's also a reason.
Which allows anyone to be able to verify without any specific requirements.
Exactly. Because in the case of Ethereum, for instance, if you want 100% censorship resistance in a very short time, you will need to run your own full node.
When we were thinking about zkVot and when Yunus was coming up with it, Matthew had shared this was one of the original ideas for an application or for a protocol when designing Mina as a base layer, but as a base layer to work with these other kind of layers. And I'm wondering if there was any other properties or if you wanted to emphasize any like specific properties that Yunus mentioned of how zkVot represents Mina well.
So I think taking a step back, a lot of zk projects, a lot of zk developer effort has gone into building tooling, building systems around voting. It's elegant in its simplicity, but given all the moving parts of this to get a successful working system, I think in part it speaks to, well, the excellent engineering effort on your side.
But also to the maturity of the tools we're starting to achieve. Not everything is easy yet, but we are getting to the stage where all of these things can be built. I think highlighting DAs specifically is useful. DAs are now becoming usable enough to do this sort of sequencing. It's also viable to start rolling things up and compressing proofs down. but it's also taken a lot for all of these things to come together. And I think we're now starting to see, for the first time in the ZK space, things are really being built successfully, scalably, and in a decentralized way.
That was the question, right?
Kind of. I think that's an important point in itself. But when Mina was being designed originally, when thinking about the application space as a whole, we see a lot of developers make mistakes, or even the way that we've marketed Mina in the past is it's an application environment where people can kind of come in and build applications the same way that they might be built in Ethereum. When you're looking at zkVot, I'm wondering if there's anything that stands out in the design, why this architecture makes the most sense for Mina.
It's interesting to pull on that thread a bit. Actually building the protocol focuses much more on making sure that Mina can support the settlement, the interaction of ZK programs, regardless of their execution environment.
You need to run some of the code locally in your browser for privacy.
You need to have some run in machines doing some aggregation, parts in the middle running elsewhere. And the really important part of Mina's design is it should support running things in all of those places and be able to pull them back together.
Ultimately, Mina should not care about your execution environment, because you need to make the right choice for your application. And zkVot is a beautiful encapsulation of this in reality. Next up, Eunice gives us an example of how developers can leverage Mina's proof of everything within their applications.
And a final thing is to use the 20 kilobyte proof inside zkVot to have very interesting anonymity use cases. So as you know, Mina is this big ZK proof of a Merkle tree. So Mina Ledger is a Merkle tree. It's a tree, and it can basically assert any state, any public key or any ZK account. So inside that single constant size 20 kilobyte proof, you can access any part of any ZK app. So let's say I have a ZK app that does KYC, and it has a Merkle tree representing all the users that are ZK KYC before. I can actually use this inside zkVot without breaking the anonymity. Basically, in the first layer we described, the voting layer, the proof will be getting the 20 kilobyte proof inside, getting the Merkle witnesses to map to that specific point inside the KYC and prove that you are inside that specific ZK app's Merkle tree without revealing your identity. That's really, really strong, especially for polling use cases. In a voting use case, you already know your voters, so you can do some pre-assertions without breaking anonymity. But in a polling case, that's not the case.
Could you quickly explain the difference between a poll and an election?
The difference between a poll and election is that in the poll, you don't know people who will be voting. You basically ask any people based on some condition, like all the people that are living in London. And if we are a ZK app that describes this property of living in London, I can actually use this without breaking anonymity in the voting layer. The other way of doing this would be getting the list of people in London beforehand, before the election, and recording them on the election contract. But that's not nice. First of all, that's really big and really poor UX. And second, that set can change during the time of pool, and that's also an issue. But this new design that we can achieve, that doesn't become any problem. Even that ZK app changes along the time, you can still use it inside the same zkVot pool.
I'll just close by saying I think given where we are in society where truth is breaking down across digital systems, this seems like a much needed tool. And to kind of like take what you just said and maybe even just simplify it a little bit, the ability to attest to and create proofs of any data that is verifiable, and then have that as an input to this voting system that's anonymous and censorship resistant and can scale to the size of the United States. This is the moment that we need this technology, but also once we have it, it will be hard to imagine a world that was before. Genuinely.